Hey guys, so I just wanted to work through the rest of the 1.4 notes with you since we are a little bit behind now. So we're just going to pick up where we left off, which is at the top of, I guess, the third page, the third sheet, where we're talking about example 6. So it says, by applying theorem 1.11, remember that was at the bottom of the page before, which says that if B is a real number and F and G are continuous at some point C, then every place that we want it, or everything that we want to be continuous is also continuous. So if we take a scalar multiple of our function, it's still continuous. If we add or subtract the two functions, it's still continuous. If we take the product of the functions, it's still continuous. And if we take the quotient, it's still continuous as long as the denominator doesn't equal 0. So for example, let's just say a couple things that would be continuous. So if we take and make a function f of x, which equals x plus sine of x, right, that would be continuous. This piece is continuous everywhere. It's just a polynomial. This piece is continuous everywhere. It's just the sine function. So their sum is also continuous. All right. Say we had f of x be 3 tangent of x, right? So again, this is a scalar multiple of our tangent function. Again, it's saying it follows that each function is continuous at every point in its domain. That's kind of a big deal. All right, we can just gloss over it and just be like, oh, it's continuous at every point, but it's saying in its domain. So remember, tangent is not continuous everywhere. We have to leave out those points where it would be undefined. So if you remember, tangent is discontinuous, or points that are not in its domain are negative pi over 2, positive pi over 2, positive 3 pi over 2, positive 5 pi over 2. Remember in class that one day we talked about saying it's every multiple of pi over, every odd multiple of pi over 2 is the spots where it's not continuous, the spots where it is, these are not in its domain. So everywhere else, this is continuous. That's still kind of a big deal though, because there are a lot of places that we have to be careful. But as long as we're not talking about an odd multiple of pi over 2, this, the scalar multiple of tangent, is going to be continuous. And then finally, we can also take this one, f of x equals x squared plus 1 over cosine x. X squared plus 1 is a polynomial. It's continuous everywhere. Cosine is one of our beautiful trig functions that's continuous everywhere. So this quotient is going to be continuous everywhere except where the denominator is equal to 0. So if you think about when cosine is equal to 0, well, that happens to be all the same places that tangent is 0, or tangent is undefined, because again, tangent is sine over cosine. So tangent is undefined when cosine is 0. So here, this function is going to be undefined when cosine is 0. So it's also going to be these negative pi over 2, positive pi over 2, positive 3 pi over 2, positive 5 pi over 2. As long as it's not one of those, it is continuous everywhere else. All right, so, but again, those all, in both cases, would be non-removable discontinuities. Again, they get around that by saying, well, it's continuous everywhere as long as it's in its domain. All right, so these are all the points where it's not, those are not in its domain. Okay, I realize that I made a typo here. This should be theorem 1.12, not 1.2. And this is talking about continuity of a composite function. Again, our function composition, we think of something like x plus 1, and then we do something to it like take the square root of it. That would be the composition of this function, the inner function, which is x plus 1, and this outer function, which is square root of x, square root. Or if we have, let's say x minus 7 and then cubed, that's our inner function, and then this is our outer function. So that would be a composition right there. So it's saying if g is continuous at some point c, and f is continuous at g of c, All right, so this would be our inner function. This is our outer function. Then the composite function given by g of f of x, which equals g of f of x, is continuous at c. So again, if we've got something that's continuous, in here, and then whatever we plug in is continuous in here, then the whole thing is continuous. All right. One consequence of theorem 1.12 is that if f and g satisfy the given conditions, you can determine the limit of a composition of functions as x approaches c to be the limit of the outer ones. Again, I feel like we talked about something like this earlier, maybe in packet 1.3, I'm not sure. But that the composition of functions still works when we take limits. Okay, so then describe the intervals on which each function is continuous. Right? So we just have to say what its domain is, and then we can say, we know from our previous theorem, theorem 1.11, that trig functions are continuous on their domain. All right? So we just have to remember what is the domain of tangent. So we just talked about that up here. So tangent has discontinuities or vertical asymptotes at all the odd multiples of pi over 2. I believe when we talked about it before, we said x is pi over 2 plus or minus n pi. That's the same as what we just wrote up there. Negative 3 pi over 2, negative pi over 2, positive pi over 2, positive 3 pi over 2, positive 5 pi over 2, and so forth. All right, so what we can say, if we're talking about the intervals on which tangent is continuous, we would just have to say it's continuous on the interval between these, and between these, and between these, and between these, right? Everywhere that's not one of these points, it's continuous on. So we would write that, let's start here and say it's continuous on, let's say, negative 5 pi over 2 to negative 3 pi over 2, not at negative 5 pi over 2 and not at negative 3 pi over 2. That's why we've got the rounded off brackets. Together with, and then we would go negative 3 pi over 2 to negative pi over 2. Again, that's the next set. And then we would say together with negative pi over 2 to positive pi over 2, together with positive pi over 2 to positive 3 pi over 2. And then at some point, we're just going to get tired of it and say, you get what I'm talking about. All right. Again, if we look at what tangent looks like, it has vertical asymptotes at negative pi over 2, positive pi over 2, and then it does something like this. And then we would have another one right here where it goes from positive pi over 2 to 3 pi over 2. And it would look like this, and we would keep going on. All right. Okay, for part B, it's asking us to say, where is this continuous? All right. So it's going to ask us to, it's going to say, let this be the function that we're talking about anywhere where x is not equal to 0. All right, again, we do that because this is fine everywhere except at x equals 0. So we're saying everywhere x is not equal to 0, let it be that. And then let's define it at 0 to be 0. All right, so we're going to end up using this one right here. All right, so we would say this is continuous everywhere except at x equals 0. So 1 over x is continuous except at x equals 0. Sine of x is continuous everywhere. All right. So this is continuous everywhere at 0. Sine of x is continuous everywhere. So again, this is kind of the composition of those two functions. So y equals sine of 1 over x is continuous. Oops, is continuous everywhere except x equals 0. All right. So then we just have to figure out what's going on right here. All right. So we would just say, actually, as x goes to, I believe we looked at, yeah, I have a note here that on page 51, if you remember what that looks like, I believe that was the one that did something like that. I'll have to go back and check that. So we are going to say that at x equals 0, the limit of g of x does not exist. All right, because again, I believe it's that one that just keeps going up and down that I made you guys graph before, if you remember that on your calculator. So g is continuous on negative infinity to 0 and 0 to infinity. All right, but at 0, even though we might define it to be equal to 0 there, the limit is not, the limit doesn't exist, and so it can't possibly be continuous there. Okay, last one on this page. How about this one right here, h of x? This one I would never expect you to get on your own, so that's why we're going to do this together. So we know that that is not continuous at 0, but does it change anything by having an x in front of it? It seems like that should not be enough, but let's just see. So using the squeeze theorem, what the heck was the squeeze theorem? All right, remember we said that to use the squeeze theorem, we have to find some function. All right, here's our given function. We have to find something that's larger than it or equal to it, and something smaller than or equal to it that we can bound it by. All right, so above, again, this is just totally clever, but not something I would expect you to use. This is always between 1 and -1. Sine is always between 1 and -1. X is always just x. So this is going to be bound above by 1 and below by -1. X is just going to stay x. So we can bound it above by absolute value of x. This might be positive in here, it might be negative in here, but if we put absolute value of x here, it's always going to be bigger than or equal to this. We could use the same logic on the bottom end and say this is always going to be bounded below by negative absolute value of x. All right, again, we know that because this is never going to go above 1 or below -1. So this is bounded above by +1, below by -1. This then is going to be somewhere between positive x and negative x. So if we take the absolute value of x, this should always be bigger than that. And if we make it negative, it's always going to be greater than that. The absolute value of x will always be greater than this, and this will always be greater than the negative absolute value of x. All right, and again, that's because this is always less than 1, less than or equal to 1. All right, so since we've squeezed this between here, then we can conclude that the limit as x approaches 0 of h of x, this thing right here, is going to 0. Why? Because we've bounded it between these two things whose limit approaches 0 as x approaches 0. All right, so we've stuck this thing right in the middle. So essentially we've got kind of this idea that our sine function is going to be somewhere here. It's bounded above by absolute value of x. It's bounded below by negative absolute value of x. Same thing on this side. And so since these two functions squeeze down to 0, this one that's stuck in the middle also has to squeeze into 0. Right? So we can conclude that because we've bounded it above and below by two things that go to 0, that this also has to go to 0. All right? So h is continuous on the entire real line. Again, the only place we're concerned about is 0 because 1 over x is not continuous there. But if we take sine of that and then we multiply it by x, it actually is continuous there because the limit exists at it equals 0, and that's what we said that we thought it should be. Right? Okay. I think that these squeeze theorem ones are kind of challenging to wrap your head around. So maybe just pause and think about that or go and watch it again. But that is what's going on there. All right, I'm going to stop this for just a second and start on the next page. Okay, so the last theorem in section 1.4 is theorem 1.13 called the intermediate value theorem. So it says f is continuous on a closed interval AB and k is some number, it's a y value because it's between f of a and f of b. Right, so we've got a continuous function on a closed interval, and k is some number that falls between f of a and b and f of b. If we have those three requirements met, then we can conclude there is at least one number c in our closed interval so that f of c equals k. Right, so let's just draw what that looks like. So let's say we've got our function, this is a right here, this is b right here. We've got this closed interval. All right, and we've got some function that looks like this, let's say. All right, so here's f of b. All right. So it goes up here, A meets up with our graph up here, so this is f of A. All right, and then I pick some value k in our function, or in this interval between f of A and f of B. All right, it really can be anywhere, and in fact, if you want to test a couple points, we can do that. But let's say that we pick k to be right up here. All right, it guarantees us that there is at least one number c in this interval so that when we pick c and we find f of c, it's going to be k. So let's just draw a cross here. All right, I actually can find several spots where that happens. I've got one spot here, I've got one spot here, I've got one spot here. So it guarantees there's at least one, maybe it's more than one. In this case where I've drawn it, I can hit 3 spots. So for example, if we call that C1, if we call this one C2, if we call this one C3, I've actually found 3 places where 3 different values of C that when I take f of that x value, I get k. Now, it's not always going to be 3. It's not always going to be more than 1. Suppose I picked k down here. Let me call it j, just so we get a different number. If I go over here, then I only find 1 value. But it guarantees that there is at least one number in this interval, closed interval a to b, that will give us that value. All right. Now, I just want to point out where things could go wrong with this, why it's important that we check to make sure that we have all the requirements met. So the big one would be if f were discontinuous. All right, so let's draw something right here. So similar to what we had, but instead of doing that nice smooth down, I'm just going to do this. It stops right here, and then it picks up again, let's say down here. Oops, I'm hitting my tripod stand. All right, so let's say it looks something like that. And this is B, and this is A. All right, so here's f of B. And here's f of A. I'm going to erase this and make the space between them a little bit more exaggerated. So let's say I pick it like here. Right, and then let's say I pick K somewhere around here. If I go out and I search for a C value that's going to get me to K, notice that it just completely bypasses the graph. All right, there is a big enough gap in here that there are certain values of k that are never going to get hit by any value of c in between here, right? So if we don't have that continuous part of the requirement, there is no guarantee that we're going to be able to find a c. Now, it doesn't mean that there definitely isn't a c. If we had chosen k to be down here, then we could say, yeah, we could find a c that would do that. Or if we chose k to be up here. But we need to know that for any k, all right, k is any number between f of a and f of b, that we can guarantee it. So if f is continuous, we promise that for any k value you pick between these two, it is going to get hit by some value c in between there. But if f is not continuous, then we cannot guarantee it. It might work, it might not work, but we cannot guarantee it. So it's incredibly important that f is continuous. All right, so let's look at applications of the intermediate value theorem. The most important application of the, oh wait, one other thing I wanted to say. The intermediate value theorem is called an existence theorem. We're going to run across a couple others of these later in the year. Existence theorems just guarantee the existence. So we are guaranteed the existence of some number c, but it does not tell us how to find it. It just promises that it exists, but it doesn't say, okay, then to find it, you have to do this. No, it just tells you that I promise you it's in there, but you're on your own for finding it, right? So a major application of the intermediate value theorem is to promise that there is a zero within an interval, right? So to say that it crosses from negative to positive, right? It crosses over the x-axis. So we're going to look at this, use the intermediate value theorem to show that the polynomial function f of x equals x squared plus 2x minus 1 has a zero in that interval, right? So in order to use the intermediate value theorem, we have to make sure that all the conditions are met, right? And again, this is what we talked about in class before, that it's that kind of thing where your mother says, if you do the dishes and you take out the dog and you pick up your dirty laundry and you make your bed, then we'll go get ice cream. If you don't do all of those things, then you can't be guaranteed that you're going to go to get ice cream. So we have to make sure that all these requirements are met in order to apply the intermediate value theorem. All right, so the first thing is f has to be continuous. All right, so is that a continuous function? Hopefully you're saying yes, it's polynomial. Polynomials are lovely, they're continuous everywhere, so check. So for the continuity part, yes, we did that. Do we have a closed interval? Yes. All right. And then the last one is k, all right, is our y value somewhere between f of a and f of b? So what value are we looking for? Well, it says that it has a 0, all right, so that means k equals 0. Is 0 somewhere between f of 0, that's f of a, and f of b, which is f of 1, all right? So what is f of 0? Well, if we plug that in, we get negative 1. If we plug 1 in, we get 1 squared plus 2 times 1 minus 1, which gives us 2. All right, so is 0 between negative 1 and 2? Check. It is. So it meets all three requirements. It's continuous, it's on a closed interval, and this value right here, that y value, falls somewhere between these two y values. Right, so what it does is it says, I guarantee you that there is a c somewhere between 0 and 1 where this function will end up being 0. Right, now, this does not factor. If we did, where is x squared plus 2x minus 1 equals 0, we could say, dang, if this were positive, then we could factor that. But it's negative, so therefore it's not factorable. We would have to use either completing the square or quadratic formula, but let's just look at what this looks like so we can see that, yeah, actually it does exist. So at 0, it is negative 1. And at 1, it's 2. It's a parabola that's facing upward, so it's going to look something like this. So yes, we can see that somewhere in between, this is f of A and f of B, that this is our value that we're talking about. This is our K value. So yes, somewhere between 0 and 1, it has a 0. What it is, we don't know. All right, again, we would have to do some work to find it, but it guarantees that there is some 0 in there. All right, so we noted that f is continuous. It's continuous on the closed interval. We showed that the value that we're looking for, 0, falls somewhere in between there. So the intermediate value theorem, IVT, guarantees that there is a C there is some value C in this interval such that f of C equals 0. All right, what that is, it's going to require some work, quadratic formula or completing the square, but it guarantees that it exists. Okay, that's it. Bye.